Hi everyone, welcome to Module 9 where we explore the difference between functions and relations and how those behave. The first definition we want to explore is that of a relation. So a relation is essentially a relationship between two sets of information. Sometimes that information is referred to as input and output, but more commonly, especially in this module, we're going to be looking at relations explored as x's and y's. So when you see a list of what we call ordered pairs or coordinates, we have x first followed by a y value. When you list a coordinate, it always has to include round brackets. So you will see things like -2, 4. You would see things like 5, 0. And again, in the first position is considered an x value, and in the second position is considered a y value in both cases. Now, the reason why that's important is because we need to differentiate between what we call the domain of a function or a relation and the range. So when we talk about domain, we're really talking about the x values, or we say the first coordinate or the input in that specific relation. We also consider the domain independent, or we consider the x variable independent when we talk about domain. Now, the other coordinate that we deal with, or the other value, our y value, is what we call the range of a function. And if range values are the y values, it's essentially that second coordinate or the output. Now, if your domain is independent, then we consider your range to be dependent. So if we look at a function, and a function is being described in this case as 3 separate coordinates or 3 separate ordered pairs, what I want to do is quickly graph those for you so that we can get our bearings on a coordinate plane and talk about things like the domain and the range. If we were to draw a graph that represents those ordered pairs or coordinates for f of x, I just want to remind you of some proper graphing techniques. So you want to make sure that you use a ruler to create your axes. And once those axes are created, we need to make sure that we label them properly as x's and y's. So we know x is the horizontal axis and y is the vertical axis. And if we start to map out these coordinates, we can, in this case, I'm going to count by twos, and you'll recognize that once I put a scale here. But I'm going to count by twos both vertically and horizontally, just so I have enough space to fit in all these points. Now, when I graph this function, or graph these coordinates rather, correction there, we want to graph the ordered pair 2, 4. So when x is 2, y is 4. We want -3, 1. So again, when x is -3, your y value is +1. And we also want to graph -5 and -6. So that would put us here on our coordinate plane. Now, we were only given 3 coordinates. We're not connecting the dots in this case. So the 3 points that you see, and I'll change the color so you can see them clearly here. The 3 points or coordinates that you see make up the function f of x. So what I want to do is describe to you what the domain and range is. So if we were to talk about the domain of f of x, and I'm just going to be really clear here and say, here's the domain for f of x, I'm going to use set notation, and it's going to include the 3 x values that are contained in that function. So we have -5, we have -3, and we have +2. So basically, we are listing all of the x values in your function. When we talk about the range for f of x, we're looking for the y values here. So if I look at the y values in each coordinate, I have 4, 1, and -6, and I would traditionally put those in order. So we have -6, we have +1, and we have +4. I'm not saying to include all of the values between -6 and 4. I'm just listing them as separate values in this particular case because we are not connecting the dots for this graph. It's 3 isolated coordinates. So if relations are essentially relationships between x's and y's, or inputs and outputs, the definition of a function takes on a very specific meaning. So we want to make sure that a function is defined as a special type of relationship in which every x or input value is paired with one and only one y value or one output value. So it's true to say that all functions are relations, but not every single relation is a function. Visually speaking, functions are going to pass something called the vertical line test, and we're going to get to the vertical line test in just a second, but we're going to focus on the first iteration of this definition and say that if you have one x or input value that is only paired with a single y value, then you have, in fact, a function. So the example at the bottom of your page here says, consider whether the following mappings are relations or functions. So I'm going to draw some mappings of x's and y's with some arrows in them to show you how the x's and y's are joined, and then we can decide whether they are functions or relations. So I'm going to make part A here a mapping of, again, we have x's and we have y's, or input and output. Let's say x is populated by the values 1, 3, and 7. The values themselves don't really matter, but maybe for y's we have something like 2, 4, and 5. If I were to draw a line that connects the input with its output, 1 might connect to 2, 3 might connect to 4, and 7 might connect to 5. What we need to decide is whether this mapping is in fact a function or is it more generally a relation. So remember, a function means that every single x or input value is only paired with one y value. So if I wanted to write these ordered pairs at the bottom, we could say that one ordered pair would be 1, 2, or there's your input output. We would have 3, 4, and then we would have the pair 7, 5. What I want you to take away from this is that our first picture is in fact a function, because for every x, there is one and only one y value. So that mapping represents very clearly a function. Maybe we have a slightly different mapping in part B. So we can still have 1, 3, and 7, and maybe we've got 2, 4, actually we'll just say 2 and 4. So if we map a 1 to 2, and we map, let's say, 3 to 4, and we map 7 to 4, once again, we have one x value, but it pairs up with only one and only y value. So if we talk about this set as the ordered pair 1, 2, 3, 4 for input, output, or xy, and 7, 4, for every x, there's still one and only one y value mapped to it. So our second picture is also a function. What I want you to think about is how you might draw a relation instead. What would that mapping maybe look like? So let's maybe see what a function looks like in comparison to a relation then. So again, if we think about x's as inputs and y's as outputs, of course, as they're supposed to be, I might have a couple of values, let's say 1 and 2 as my input. But when I take a look at my y values, I'm going to list several y values in here. If I map 1 to 3, and I map 1 to 5, what's happening is we have the same input with two different y values or two different outputs. As soon as you see the same x mapped to two different y's, what you know is that it's not a function. In fact, it's a relation. Now, it doesn't matter how we map to, we already have something that is not a function. So we would label this diagram at the top of your page as not a function, and if it's not a function, we in fact just call it, therefore, a relation. So remember, a relation is a general type. It means we're talking about a relationship between x's and y's. Functions have to be specific. For a function, we have to make sure that every x has one and only one y value paired with it. The next example, instead of giving us a mapping, gives us a set of coordinates or ordered pairs. So we're given x's and y's of 2, 3, 4, 3, and 2. If you'd like to create a visual, you can create a mapping here, but remember, if this is a function, then every x is only mapped to one and only one y value. So if you pay attention to those x values, all three of these x values are different. So I don't have the same x value mapping to two different y's. So because of that, I can say that this is in fact a function. If we look at our next set, we have the ordered pair 5, 1. We have another ordered pair 6, 2, and then we have a third ordered pair of 5, negative 3. Now, if I look at my input or x values, what I want you to notice here is that 5 appears twice. The same x value actually maps itself to two different y values. So there's a 5, 1, or a 5 that maps to 1, and there's a 5 that maps to negative 3. So because the same x value maps to two different y values, we say this is not a function, and in fact, it's a relation. Sometimes students like to draw those mapping diagrams to be really clear, or you can plot these points on a grid and see if those points pass something called the vertical line test. So we made mention of the vertical line test just a moment ago, but I want to show you the vertical line test up close with our next example. So the next example, or example number 3 on your screen, reads, examine the following graphs and determine whether they are functions or relations. So I'm going to draw a bunch of pictures for you and explain further how the vertical line test works. So according to the vertical line test, if you have a function and you run a completely vertical line across any point on a graph, it should only cut the graph in one spot. So if I were to draw a vertical line, let's say here, pretend that's perfectly vertical, perfectly up and down, I would only be crossing one point on the graph. If I moved over, let's say further to the right, and I drew another vertical line, again, I'm only crossing one point on that black graph. If I move even further to the right, again, I'm only crossing one point on that black graph. So this is passing what we call the vertical line test. So because this passes, so if you can imagine that vertical line moving from left to right, it passes the vertical line test because it only ever cuts one point on the graph at a time. And because it passes that vertical line test, we can therefore say this is in fact a function. If it fails the vertical line test, then we have a relation. So let's take a look at our second graph here, right in the middle of your screen. If I were to draw another vertical line, again, I'm only cutting through one point on the graph. If I move over a little bit, again, I'm only cutting one point on that black graph. If I move even further to the right, again, I'm only cutting one point on the graph. So this, once again, is passing or passes the vertical line test. Therefore, we can say this one is also a function. What we're seeing here is that every x coordinate is only mapped to a single y value. So it's basically 1x to 1y. In this last picture, as soon as I draw a vertical line, things look a little bit different. What I recognize here is that with that vertical line, I'm cutting through two different points on the same grid. As soon as I cut through more than one point on the same graph with a vertical line, I fail that vertical line test. So this last graph fails the vertical line test. Therefore, it's not a function. We say instead this is a relation. So basically, you can imagine that for your x value, you would have two different y values. You'd have one that was positive or on the top side of that graph, and you'd have a y value that was negative given the same x coordinates. So once again, if you pass the vertical line test, you have a function. If you fail that vertical line test, you have in fact a relation. So far in this lesson, we have looked at functions and relations. We have domain and we have range. Again, domain are all the x values included in a particular function, and range are all the y values or output values that are included in a function. But we need to distinguish between what's called discrete data and continuous data. So discrete data is basically countable data where points are not joined. So if you drop points on a coordinate plane or on a grid space, you can't connect the dots if they're considered discrete data points. When we talk about the domain and the range of discrete data, we need to make sure that the x and y values come from the ordered pairs or the points on the graph. Domain or range is only going to include a list of values in this case, where that's not always the case with other kinds of continuous data. And we'll get into that in just a moment. So when you have discrete data, basically we just want you to draw those points, and we want you to be very mindful of how things like the domain and range are listed. So I'm going to give you an example of some discrete data. We're going to graph it, and then we're going to decode what the domain and range is for that particular graph. If I were to define a function, let's say f of x is equal to 1, 2, 2, 3, and the ordered pair 3, 0, let's say. Let's first map that out. So if I change colors here, I've got the ordered pair 1, 2. We can see that this grid is already labeled and ready to go. We have 2, 3, and when the last point we have is 3, 0. So I have 3 dots here. Because this is considered discrete data, I'm not connecting the dots. I don't want to make a triangle or some strange sort of function out of this. What I need to do is just consider that these 3 input and output pairs are separate. So if we wanted to ask you to determine the domain of this function, again, it would be just a list of all the x values. So my x values are 1, 2, and 3. But it wouldn't include anything between those values. So I wouldn't say, 1.5 is included, or 2.5 is included, or any of those fraction values between 1 and 3. The range of this function, on the other hand, are all the y values, or the output values. And if we put it in increasing order, I have a y value of 0, a y value of 2, and a y value of 3. So this is how you have to make notation for domain and range for discrete data types. Again, we don't connect the dots, and we list the values inside that domain and range. Data that's not discrete can be considered continuous. So continuous data are essentially data points that are joined. Usually, these are somehow associated with a type of physical measurement. So data of this type, if it's continuous, includes all of the values between your 2 endpoints. So basically, we're looking at every single possible fraction, decimal, rational, or irrational number between a start point and an end point. Again, when we're talking about domain of a function, we're talking about all of the x values starting at the left or far left side of your graph, and we continue to the far right side of the graph. Range, on the other hand, I always say is low to high. These are the y values, and we want to start figuring out those lows, or the beginning of our range, at the low point of your graph, and you continue to the highest point. So domain is always left to right. Range is always bottom to top. So we're looking at either x values covered from left to right, or we are looking at all the y values covered or included from bottom to top. So example number 4 on the next slide says graph y equals 2x plus 3 for x equals -2, 0, and 3 only. Then we want you to state the domain and range. So because they're saying x is only -2, 0, and 3, we know that this is considered discrete. So we can still build a little table of values. So we have x on one side, and then we have, on the other side of our table, we have y, which we know is equal to 2x plus 3. So that's how we're going to figure out what our y value is. We're told that x is -2 initially. So if we make a substitution, then we know that your y value is going to be 2 times -2 plus 3, or -4 plus 3, which we know to be -1. If x is 0, then we have 2 times 0 plus 3, so we're just making that substitution. And when we simplify, 2 times 0 is 0, 0 plus 3 is 3. Last but not least, we have x equals 3. So 2 times 3 is 6, plus 3 more is going to be 9. So basically what we have here are 3 ordered pairs that we need to graph. We need to graph -2, -1. We need to graph 0, 3. And we need to graph 3, 9. So because these are considered discrete data points, we want to graph them, but we don't want to, in the end, connect those dots. So because I have to go as high as 9, I don't have a very big scale here on the axes that I've drawn. So I'm going to count by 3s vertically. So there's 3, 6, and this is going to be 9 up here. So if we go this way, we have -9 at the very bottom. We can count by 1s horizontally as well, because we don't need too many ticks to account for all of the values we were given in the table for the x's. So my first ordered pair is going to be -2, -1. So when x is -2, y is -1. Just be mindful of our scale here. I'm exaggerating these points so that you can see them. We also have 0, +3. So that's going to be your y-intercept at that location, and then we have 3, 9. So when x is equal to 3, my y value is 9. So what we need to do now is leave our graph alone. We're not supposed to connect the dots because this is discrete data. So if we want to determine the domain of this function, the domain is going to be the 3 x values that are included from left to right. So my first x value is -2. My next x value is 0, and my last x value is +3. So there's the domain of this set. Now for range, we're talking about y values, and we have to think low to high. My lowest y value happens to be -1, so we're going to start there. My next y value is going to be +3, and my last y value, my highest y value in this discrete data is +9. So I've listed all of the values of my domain and range. So the difference between question number 4, which you see on our board here, so this is for question number 4, and the next question, question number 5, says go ahead and graph y equals 2x plus 3, where x can actually be any real number in the whole wide world. So what we can do is actually cheat a little bit and use the 3 values that we already have marked in place. The same table of value fits because it's the same equation, but I'm just going to add or sneak in maybe one more value here. So let's say maybe x is equal to 1. And I know my table's out of order right now, but that's okay. We're just finding another point. So if we have 2 times 1 plus 3, 2 plus 3 is going to give us 5. So we have another ordered pair of 1, 5. If I draw that one more ordered pair in here, this is about where it sits. Now, if I could choose any x value in the whole wide world, if I really wanted to, I could choose an x value of 1.5, or I could choose an x value of -1 or -0.7. I could choose any x value I want. But what you're going to notice is that this is a linear function, right? It's a straight line. So if I were to connect the dots, and I'm going to do this the best I can with the technology that we have here. If I were to connect the dots now and make a linear function, again, it wouldn't matter what I chose for x. They would all fall on the same line. So this is the graph of my function y equals 2x plus 3 when I'm allowed to choose any x in the whole wide world. So if x is any real number. What that does is it changes how we write the domain and the range because we're supposed to connect the dots here. So when we think about the domain, I want you to think about how far left this graph is going to reach. So if we keep tracing and we keep tracing this line further and further and further to the left, I'm going to go further into the negatives, but we're not talking about down, we're talking about further to the left. So my domain is going to start at -infinity. So it reaches from -infinity all the way to the right. Again, as far right as we can imagine, we have +infinity because we're talking about this tail here, not because that tail is going up, but because that tail is sneaking further and further to the right. When we think about the range of this function, of course, range is low to high. So the lowest point or y value on this graph is going to be negative infinity. And the highest y value or highest y on this graph is going to be positive infinity. So the domain and range are going to be marked very differently whether you have discrete data or whether you have continuous data. That brings us to the end of 9.1, folks. Please have a look at these homework questions and do some practice problems. If you find that you've got any points of confusion, don't hesitate. Make sure you reach out as soon as you can and we can help you get this sorted.